In a previous video, we had discussed how polarity of a molecule can influence whether it will mix with another molecule or not. Just a reminder that if a molecule is polar, then it will also be attracted to polar neighbors, for example, water and alcohol. However, if a molecule is nonpolar, then it will not be attracted to polar molecules like oil and water. Nonpolar molecules, on the other hand, would tend to attract other nonpolar molecules. What is the reason that a polar molecule is attracted to another polar molecule? Well, it's very similar to how two magnets are attracted to each other. If you think about a bar magnet, it has two poles, just like a polar molecule. It has a north pole and it has a south pole. A polar molecule, like water, for example, has a negative end, which is on the oxygen end for water, and then a positive end, which is on the hydrogen end. And if you have a bar magnet, the south pole of a bar magnet would be attracted to the north pole of another bar magnet. And that interaction is what keeps the two magnets together. Similarly, if you have two water molecules, the negative end, which is oxygen, and the positive end would be attracted to each other in neighboring molecules. So in this case, we have an oxygen from this molecule on the right, and that's attracted to the hydrogen from the molecule on the left, and that interaction is what's keeping the water molecules together. This type of interactions is what we refer to as intermolecular interaction, and the type of force that's holding them together is called intermolecular forces. This is the type of interactions that keep a substance in a condensed state, for example, a liquid or a solid. Now, once you're in the gas state, you're breaking all this interaction so the molecules are separated and become individual particles. But in the solid and liquid state, they're stuck together by those intermolecular forces. So what is the basis of the intermolecular interaction? Well, those interactions really come about because each molecule can be thought of as a dipole or having two poles, just like a bar magnet is. So there's a negative end and then there's a positive end. The only difference between the different forces that we're going to talk about is just whether the two poles are strong and permanent or whether they are weak and temporary. And so we're going to start with the weakest of the intermolecular forces that you're going to encounter. And that weakest one is called London dispersion force. This is really a type of intermolecular force that only exists for nonpolar molecules. And the reason is because nonpolar molecules are not dipoles. They don't have positive and negative end because nonpolar means that the electrons are distributed uniformly across the entire molecule. So there is no part of the molecule that is more negative. There's no part of the molecule that's more positive. So how do they form intermolecular interactions? Well, the way it works is as follows. So let's say you have a nonpolar molecule, for example, helium gas. The electrons are completely uniformly distributed throughout the entire atom. Now, as helium gas goes through different environments, these two valence electrons are circling around randomly distributed in these electron clouds. Sometimes, just by random fluctuation, the two electrons might end up fairly close together compared to when they're in this position where one is on this side and the other one on that side. That's a fluctuation, that's temporary. But when that happens, this side of the molecule is going to be more negative, so we put the delta negative sign, and then this side of the molecule will be more positive, so we put the delta positive sign. When your molecule have those negative and positive poles just temporarily, what that allows this atom to do is to influence the neighboring atom. Because this side now is positive, that positive side of that atom is going to attract the electrons on that neighboring atom. And as a result, the electrons that's kind of randomly floating around, it's going to be pulled towards this side, making this second atom now negative on this side and positive on that side. Once that happens to the second atom is going to influence a third atom to move its electrons to this side, making this one now negative and positive, and go on and on just like that. So as you can see now, because we have a positive and a negative, these two can make interactions with each other, thereby holding them together. Now these interactions are really weak because the source of that dipole is temporary. These dipoles can disappear with changes in the environment, so it's not really permanent dipoles, and therefore that interaction is really, really weak. And that's why helium is not going to form a liquid until the temperature is very low, because that interaction is just not very strong. It's easily disrupted by the movement of the atoms themselves. Now we're going to move on to the second type of force, and this is called the dipole-dipole force. So dipole-dipole force exists in all polar molecules. So remember, the first one we talk about is only for nonpolar. This one is for all polar molecules. Polar molecules, by definition, have two poles. They have a dipole in the molecule itself. So here's an example. Here's a molecule that is carbon connected to an oxygen and then two hydrogens, which are the white atoms here. So the oxygen, as you remember, is a fairly electronegative atom. So then the electrons are going to be pulled towards the oxygen. So the oxygen side of the molecule is going to be delta negative, and the carbon side of the molecule is going to be delta positive. So that dipole permanently exists in that molecule. It's not temporary like the case with helium, but it's always going to be there. Because the dipole is there, that means if you have another one of these guys floating close by around, the dipole from this first molecule is going to interact with the dipole from the second molecule, thereby forming this dipole-dipole interaction. And so there's just one dipole from one polar molecule interacting with a dipole from another molecule. The third one is something we call hydrogen bonding. The way I think about hydrogen bonding is that it's a super dipole-dipole force. It's just a stronger version of dipole-dipole. The way you know that a species can have hydrogen bonding is when you see a molecule that has a hydrogen atom that's covalently bonded to either fluorine, oxygen, or nitrogen. Let's take a look at HF. So HF itself is a dipole. We know that because F is an electronegative atom. So the fluorine side of the molecule is going to be delta negative. The hydrogen side is going to be delta positive. If I have another HF nearby, then this one is also going to be delta negative and this one is going to be delta positive. And those dipoles are permanent, so now they can make these interactions, which is illustrated in these dots right here. And that interaction is what we refer to as a hydrogen bond. So why is hydrogen bond stronger than your standard dipole-dipole? Because both of them are permanent dipoles. They're both polar molecules. One is that due to the size of hydrogen, it allows the two molecules to come closer together. The closer the interaction, the stronger it's going to be. Just the same way as if you have two magnets that are closer together, you're going to feel more attraction between those two magnets than if they're separated further apart. The second is that because hydrogen is small, it's a lot easier to cause their electron cloud to be distributed asymmetrically, meaning that it's going to be more positive and the interaction is also going to be stronger. Again, comparing this to magnets, it's like having a bigger magnet, a bigger north pole on this side. Well, that's obviously going to pull on the south pole a lot more strongly. Okay? All right. So one thing I want to point out right here is not to confuse these two terms, which is intramolecular interaction versus intermolecular interaction. So intra means that the interactions or the bonding occurs within a molecule, whereas inter means that the interaction occurs between molecules. So what are examples of intramolecular interaction? Well, the main one is a covalent bond. And you can think of ionic bonds as intramolecular as well, but the main one is covalent bond. So for example, if I look at this HF molecule, the bond between this H and this F is an intramolecular interaction. It's a bond that exists within that same molecule. This H and this F is part of the same molecule. The intermolecular one is the interaction between this F and the H from the second molecule. So that red dots represent your hydrogen bond, which is your intermolecular, because that's between molecule 1 and molecule 2. So hopefully that makes sense, the difference between intra and intermolecular. Hi everyone, I want to work through a couple of examples of identifying intermolecular forces in different types of molecules. I'm going to just pick a couple of these molecules to illustrate how I would go about determining the type of intermolecular force that exists. So the first one I'm going to look at is CH4 right here. And the way you do this is you have to first draw the Lewis structure. And hopefully you're fairly comfortable in drawing Lewis structure. So for CH4, it would end up looking something like that. And the next thing to do is to determine molecular polarity. For this structure right here, this is going to be nonpolar because all the bonds are nonpolar bonds. So this is a nonpolar molecule. molecule. So once you determine that it's a nonpolar molecule, then there's only one choice for intermolecular forces, and that is the London dispersion force, because that's the only type of intermolecular force that exists in nonpolar molecule. Okay, let's take a look at another molecule, which is CH3OH. And if you draw the Lewis structure, it would end up looking like this. And then step 2, determine molecular polarity. This particular molecule has two central atoms, this one and this one. So the two central atoms are not identical, and the ends of these, obviously this has a polar bond between C and O and H. So therefore we would conclude the overall molecule to be a polar molecule. Once we determine that it's polar, there are two options in terms of intermolecular forces. Either it has dipole-dipole, or it has hydrogen bond. And to determine which one, we have to look at the actual bonds that exist in the molecule. There is an OH bond, and OH is one of the covalent bonds that can make hydrogen bonds with other molecules. So this is a hydrogen bond. And then if you look here, you see that there is CO, and that's a polar bond, which means that this can form a dipole-dipole interaction as well. Now, when you have multiple interactions existing in the same molecule, then what you have to determine is which one is the strongest one. So since hydrogen bond is the strongest one, we would say that this molecule, the major intermolecular force is hydrogen bond.